Hey everyone, my name's Andy and I'm co-presenting with Davin today. We're talking about observability for configuration management and compliance. So, who the hell are these people, and why should you listen to us? I was a Chef employee from 2015 to 2022. I started in our customer engineering group and really helped customers along their DevOps and config management journey. Also spent about 5 years before that at BlackBerry running some really large systems. You might call them complex systems. And eventually, through my time at Chef, I ended up running the customer success group or helping run the customer success organization. And we're really focused on making sure customers were kind of hitting as close to peak DevOps as they could. And then, I've spoken at multiple ChefConfs. I've spoken at International DevOps Days. And recently I spoke at Ollie Fest. We might say Ollie a few times here. It's O11Y for the 11 letters, and it just stands for observability. And currently I'm at Honeycomb working in customer success group. Davin, you want to introduce yourself?
Yeah, hey, I'm Davin Taddeo. I have been sort of a lifelong nerd, working operations work prior to joining Chef in 2019. I was there both as a professional services engineer and as a customer success architect up until 2022 when I moved over to Honeycomb. Currently just working on helping customers get better visibility into how their applications function, and right now trying to translate some of that knowledge of observability back into the world of DevOps and config management.
Thanks, Davin. So really like to start all of our talks with who's this for? That way, if you're like, hell no, that ain't me, you can make that decision and get out of here. So, we're not going to bring anything groundbreaking or new to Chef or Inspec with this talk. We're really focused on how do you get more out of the data you collect from it, and some cool things we created alongside that. So the talk's going to end up being a little more theoretical for the first half around what is observability, why should you care about this, why should you get your Chef and Inspec code into an observability tool. Davin and I do work for a tool that is in the observability space. So when we get to the technical side, we have chosen to show that in our tool, but you could do this with any observability tool that you choose. You might have to make some changes to the things we've written, but overall, you could do similar things. And really, the question we're trying to answer here is, you have a lot of data stored about your Chef and Inspec code. You've got it in a really cool system called Automate, probably, which is great for finding data about specific runs and about auditing and holding onto that data for whatever period you need to hold it. But how do you find it and ask questions about it really quickly in the moment? That's really what we're trying to talk about and get to here. And we've said observability a few times. Observability is really about being able to make sense of complex systems. It's when a system achieves a state of you being able to ask or interrogate the state of that system merely from its external outputs. And software comes in various forms. Traces are one example of that. There's other ones like metrics. A lot of monitoring tools provide some input into observability, but we're going to focus a lot on traces today and how you can make use of traces with your Inspec and Chef environments. Observability is really about being able to ask arbitrary questions about your system without having to know ahead of time what you want to ask. You should be able to find answers to those questions, even ones you didn't know you needed to ask, or we call those the unknown unknowns, without changing the system or deploying new code at any given time. This really requires you to store data about your environment well beyond just like a pass-fail of a specific resource or control, and you really need to be able to find unique high cardinality information. So high cardinality being a field that could have a lot of different values, like employee ID, customer ID, that kind of thing would be high cardinality. There's only going to be one customer with that ID, and you want to be able to find information based on that. Something in the Chef and Inspec space would be like, hey, in an Inspec profile, you have a control ID. That's going to be fairly unique. It would be good to be able to sort information based on that, or host name. Host name is a good one too. We mentioned complex systems a little bit, and I just wanted to define that. And really, a complex system is defined as any system that is too complicated for any one person to understand the entire state of any at any given time. The there's, as a side story, a few years ago, another chef employee named Galen Emery and I kind of watched the Chernobyl mini docudrama that was out on, I think it was HBO back in 2019, and we're like, this is really cool. How does this apply to computer systems and technology systems today? And we actually went on this path of, we both submitted talks to different conferences, but with the same topic, just with him with a little more of a focus on compliance and things like that, and me with a little more of a focus on complex systems. So if you go back and look up, I think it's called unanticipated interactions of multiple systems. We both did a talk called that. If you Google it, you should be able to find it. And it's just a cool thought experiment on how two people ended up making similar but different presentations. So we're going to talk a little bit more about complex systems here over the next, say, 15 minutes or so. I had a lot of influence from 3 different people on this. There's a book called Normal Accidents by Charles Caro. There's a book called Drift into Failure by Sidney Decker, and a presentation by John Allspaw, who a lot of people here may have seen talks from, called How Your Systems Keep Running Day After Day. And the common theme across all of them is that accidents are going to happen. System failures are normal, are expected by nature, and that things evolve, that systems, technologies, things that get built evolve both based on the technical changes as well as the socio-economic factors that influence them. So highlighting that, complex systems are going to fail. On the left here, we have a jack screw from a airline that crashed. And on the right, we have the consequence of a AWS major outage, which is people pushing for a decentralized alternative to AWS. Those are consequences of failures, but failures happen all the time. And we mostly understand the world from linear interactions and component failures that got defined by Descartes and Newton. And that Cartesian Newtonian paradigm proposes that we can analyze problems from the analogy of a machine where, knowing the operation of the isolated parts, it's possible to be able to understand the whole formed by those parts. So basically, by going and studying all the individual pieces of a machine, you can go and understand the entire machine and the output of that machine. And in a complex system, that's simply not possible because no one person is going to be able to understand all the individual parts. That kind of traditional thinking has led us to society looking at accidents from a couple of perspectives. One being the amoral calculator perspective. For instance, the airline reduced their maintenance interval. That was obviously bad. Or the mechanic didn't complete the right service. That caused a failure. In addition, we use rational choice theory to understand the decisions people and organizations make. And rational choice theory says that operators and managers and other people in organizations make decisions by systematically and consciously weighing all possible outcomes along all relevant criteria. They know failure is always an option, but the cost and benefits of decision alternatives that make such failure more or less likely are worked out and listed. Then people make a decision based on the outcome that provides the highest return on criteria that matter the most. The rational decision maker will know all possible alternatives and which course of action will lead to which alternative. They're capable of an objective, logical analysis of all available evidence on what would constitute the smartest alternative. And they're fully rational and able to rank the alternatives according to their utility relative to the goals the decision maker finds important. Now, I said a lot of words really quickly there, but I don't know anyone in the world that would actually fit all of those categories. So, especially as the system gets more complex, there's no way for you to know the outcome of a possible alternative choice which was made previously. You may not even be aware of all the choices that get made on a system. And no one is fully objective. Companies often put people at odds with themselves: faster, better, cheaper. Like, you can't have all 3, you've got to pick 2. As you're going through those decision-making agendas and meetings and things like that, you're going to weigh the ones that are more important to you inside of an organization. And that's going to sway a system or sway a complex system in one direction or the other. Pictured on the left here, we have the jack screw from Alaska Airlines Flight 261, which crashed on January 31st of the year 2000. This accident happened after a maintenance window in which a mechanic inadequately or not at all lubricated the jack screw. Who do you blame in that case? Is it the mechanic's fault, the supervisor, the airline? If we were live in person, I'd ask that question and we turn it into a short discussion in the room. In this world of virtual conferences, we'll move along. But it is important to note that it was an overnight maintenance, it was cold outside, and there was bad weather. Inadequate protection was available for the mechanic, and the access panel to maintain the jack screw was difficult to reach even on a good day. As well, the maintenance interval for that jack screw changed drastically from the 1960s when the plane was initially designed and delivered to the early 2000s when the incident happened. In the mid 1960s, you were at 300 to 350 hours between maintenance that would lubricate that jack screw. By early 2000, there was no more flight hour requirement. It was simply every 8 months. That part showed no lubrication for over 5,000 hours. That's one missed maintenance in early 2000. If you were still at the regular maintenance schedule, there would have been 16, 17 chances for someone to catch that and lubricate it back in the 1960s. And it's important to note that the airline industry is fairly regulated or is at least fairly monitored. So this maintenance guideline was agreed upon by both the NTSB and by the airline industry. So why did this deficiency not strike anybody as a deficiency at the time? Why was no one persuasive enough to convince people it was a deficiency? You can't tell me that the engineers making these decisions or reviewing these timetables, if they thought it was a deficiency, wouldn't have tried to persuade people not to do this. Why did the regulator not stop it? Why did the NTSB allow the airline industry to change this maintenance so drastically? People must have found things acceptable at the time they made the decisions. Organizational trade-offs, decisions that seem normal, deregulation, they all put increasing pressure, including competitive pressure. In the case of deregulation, you get more airlines trying to operate for the same business. They put more pressure on decision makers over years and years. And the people that made the decisions to increase the maintenance windows may not have even known about decisions made prior to them. As an example, in 1985, as an accompaniment of deregulation, the airline industry, we moved that check to every 700 hours or every other maintenance B check. In 1987, the B check interval was increased to 500 flight hours, which made that turn into a 1,000-hour interval. In 1988, B checks were eliminated and tasks were distributed to every 8th A check. And A check and B check is just lingo in aircraft maintenance terms. A checks happen more frequently and B checks happen less frequently. And basically, those B checks were completely eliminated and tasks distributed to every 8th A check. This actually kept it at 1,000 hours, but in 1991, A checks extended across the industry, moving to 1,200 hours. And it's important to note there that no one said, hey, let's move that jack screw lubrication to every 1,200 hours. The maintenance window was just changed. Did someone make the conscious decision to actually change that specific maintenance? We don't know at this point. And finally, in 1994, A checks were extended across the industry to 1,600 hours before the flight hour requirement was removed completely. This maintenance was missed on an 8-month window, and the aircraft flew for more than 5,000 hours without a lubrication of a critical part. Now, why do we bring this up? Why are we talking about airlines in a technology conference? It's because the more complex the system gets, the closer you get to becoming an airplane. Your IT landscape is becoming more complicated by the day. Complication will eventually lead to complexity. Complex systems are becoming the de facto design for services. See Lambda, Cloud, Kubernetes, etc. Every time you layer something on to your system, it becomes more complex. I bet that most people's systems here look pretty similar to something that looks like this. The addition of regulatory and socioeconomic factors into your work stream and processes also breeds way more complexity over time. We're just talking about technology for the most part here, or mechanical parts. We didn't even get into the socioeconomic factors that can affect things here. As your system gets more complex, the stuff below the line on the last slide becomes much less visible to people and becomes much more abstract. You end up just seeing the things that are above the line. This is how you interact with the system. This is the way you look into the system. You can no longer model and troubleshoot the system in your head. Your information and reasoning about the system only come through the lenses you have into the system. And that's through an increasingly few key points, including source control, your CD pipelines, your observability system, and your audit logs. We've actually done this kind of troubleshooting for a long time, interacting with systems like this. If you've ever troubleshot an issue and reached the conclusion, hey, this is probably a networking problem, you were probably using the logs on your server and noticed strange behaviors pointing at the network. Maybe you ran a TCP dump, maybe you started looking at things, but you realize, hey, something outside of my control is messing up and I need to engage another team or I need to go look at another place. The logs were your window into another part of the system you don't have direct control over and likely don't completely understand. This level of abstraction is only becoming amplified as systems become more complex. So, like the amount of times that you're actually logging onto a server and looking at logs on like a container running in Kubernetes on a pod that is running one instance of a microservice is becoming less and less likely that that's how you troubleshoot a system. You're more likely troubleshooting it and looking at it through a window of monitoring and telemetry. So at the end of the day, complex systems should be and have to be observable in order to make sense of them as they get more complex. And there's a few things we know. Complexity isn't designed, it evolves, so it gets layered on. For example, you deploy on VMs, but hey, now you've migrated half your infrastructure to containers. Now you've got this like half and half solution going on. Your goal is to eventually get to containers. It's going to take 2 years. And hey, there's a whole new set of things over there that no one on the team understands yet. And let's face it, if you're running on like EKS or in a public cloud, you're probably never going to understand the entire thing. Modern systems are simply too complex to be fully understood by a single person in like a Cartesian Newtonian paradigm where you understand all the parts of the system to gain an understanding of the whole. Relationships between components are nonlinear and can even become circular. We're working on a service map feature here at Honeycomb, and trust me when I say the service maps of real systems, even the smaller ones, are decidedly non-linear today. And the causes of today's incidents will not be the causes of tomorrow's, and dashboards based on today's issues will essentially be useless when they can't answer the new questions you have tomorrow during that outage. Cause and effect are usually obvious, but only after the fact. So, you're going to be able to tell like, hey, that we under provision this part of the system, but you won't know that in the moment until you get enough data to figure that out. And despite having data before them, people refuse to believe what they see. There's a story about NASA engineers that were working on the Space Shuttle Columbia when its disaster happened, and they didn't believe the sensor data that they saw until someone turned on the TV and they saw the news report of something, of a fireball and something happening over Texas. And finally, they stepped outside and looked up and could see, what was happening and believed their sensor data at that point. The more signals and data we can give people, the better chance they'll see the picture. It's time to give yourself the insight and observability into your configuration management data so it can be part of the other windows you have into your system. I've talked a lot about the challenges with complex systems and the fact that a lot of us are running complex systems now. I wanted to talk a little bit about, solutions and ways to approach them before we get into some more of the Chef and Honeycomb specific stuff. But in a complex system at any given time, especially in an incident situation, there's no objective way to determine whose view is right and whose view is wrong. You can only really tell that after the fact, once you've actually pinpointed what the problem is and fixed it in some way, shape, or form. Your best chance at reducing accidents in a complex system is actually diversity. And by that, I mean diversity of race, culture, gender, language, background, experience. The more diversity you have, the greater your ability to generate different and inventive solutions. And you can't just have diversity. A diverse group of people need to be listened to, respected, and have a say in the design, the possible actions out of an incident and during an incident. Any investigation that happens needs to reorient around the new state of the system. That dashboard you created 3 days ago about an incident that happened in the past may not and probably is not relevant and may not even feed into a future incident. Stop thinking about the system as a snapshot in time that you need to go back and find the input that caused the output to fail. In a complex system, that input and output may not exist anymore. And after the incident, the same input may not cause a failure. It's important to know what caused an incident, but you have to understand that the future instance could be caused by the same or completely different things. And make sure to pay attention to the socioeconomic and other non-technical drivers that contributed to any incident at any given time. I'm going to stop sharing and pass it over to Davin for a little bit here.
So moving right along, talking about complex systems being observable and knowing that our dashboards probably aren't good enough because in a complex system, because again, as Andy said, the problems of yesterday are unlikely to be the problems of tomorrow. And we don't know what the problems of tomorrow are going to be. There are lots of things we don't know. So we need to be able to have the data to find out what the problem is tomorrow. And therefore, we want to make our system more observable so that we have more high cardinality data that we can look at the picture of our systems today and query it and understand what's going on so that we can react effectively and so that we can know more about our environments and know more about this, these large socio-technical complex systems that we're developing. Right now, if we look sort of a little closer and just at metrics and stuff like that, a lot of current tooling, even around Chef that we have now is very much the picture of pass fail. Having more data allows us to look beyond that. We can filter that data by, say, node attribute and stuff like that. We want to find, for instance, all instances where a specific inspect control is failing. That's a difficult process right now, but with a quality observability system that has, a lot of data that you can query, you can do these things. So, why do we want to observe Chef and Inspect? We want to be able to report on the knowns. Obviously, you want to know how many systems are running Chef or Inspect. You want to know how many cookbook, how many Chef runs are failing, how many Inspect controls are not passing. You want to be able to find the unknowns. You want to be able to see the correlations between, platform and, what platform you're on and what controls are failing, or you want to be able to find out, what nodes are failing multiple times in a row or something along those lines. You want that observability because that will give you a chance to improve the system. Chef and Inspect allow us to work across the entire complex system in our environment. And so, finding the components of those policies and those profiles that don't work very well allow us to improve that code and improve the way that our system functions and the way our system is maintained. It also helps us find where there might be conflicts with other systems or potentially just users managing systems and breaking things they're not supposed to. So, these are some of the reasons we want to observe Chef and Inspect, but also things like finding long running or noisy resources in our code, stuff like that. That's the building better code part. So when we talk about observability tools, we're going to talk about Honeycomb here. What is Honeycomb? Why is it suited for this? So Honeycomb is basically a behind the scenes, it's a big column store database that is holding billions and billions and billions of rows of data, of high cardinality data that represents the experience that users have utilizing your applications. So in this case, Chef and Inspect, we can host, we can have thousands of columns of very useful information that you can query very, very quickly to help you get better uptime, better success rates, better understanding of your systems, and understand sort of where these, determine where you have your high performance markers, where you want your systems to be at, and also, and allow you to really target how you work towards hitting those high performance goals. So that said, I'm going to jump into a demo here, show you a little bit of the Chef code Chef handler code that we wrote for this, as well as how we look at that data inside Honeycomb. Jumping in to the right code here, what we have is a Honeycomb handler code, which basically is giving us data in a JSON format that we can transmit to Honeycomb that will show up at where each Chef client run will show up as trace data that can be observed and queried and analyzed within the Honeycomb product. We're doing things, catching some, we don't capture every single node object just because that is a lot of data, and a lot of it is stuff that people don't really care about. But, things like node name, Chef version, OS, platform, host names, all those things, some of your config values like your Chef server URL, if you're running a named run list, we get, a few other things in there as well. I've got a little bit of code so that we can actually calculate a link to automate about each specific run that a trace represents, Chef client run that a trace represents. And basically it turns that around, spits it out, sends it to Honeycomb, and there we can analyze it. The way that we gather that data is using the chef.event handler method and in our recipe, and we recognize all of these various events that are part of the Chef client run process. And then we capture data out of those events. We then send that on to the handler. The handler sends it on to Honeycomb. There's a little bit of setup to utilize this. You've got to have your Honeycomb API key. You want to know the data set or database name where you want all this data to live. If you do want to generate and automate link to your Chef client runs, you have to put in your automate FQDN. The other thing that we allow is that if there are specific node attributes outside of the standard ones here that we define, that we've defined, you can set up your own node attributes that you want to track and make sure that those go into Honeycomb. So if there's specific like application attributes, or if there's specific attributes for your specific ecosystem, technical ecosystem, then you can track those here. Once, if you want to look at that inside of a recipe, I've got this ChefConf cookbook and policy. Basically, I have the same event handler code here. I didn't get a chance to sort of abstract it by calling it into a policy file, but then I make some files. I make a decision on whether or how long to run a chef sleep command, and then arbitrarily fail based on a random number generator. I also call one of the DevSec OS hardening cookbook and run that as well, just so we can get more resources in the trace and we can see how it sort of looks out. So all that comes together into Honeycomb, basically to look similar to this. And this isn't super impressive, I know, but what you're seeing here are you're seeing all of the Chef client runs for the last 2 hours. The peak number of concurrent Chef client runs apparently is 7 right now. But that's not a ton of data there, but we can actually improve that view. So I want to know what my actual number of chef clients exist, for instance. So I can look up the GUIDs. I can do a count distinct of all the GUIDs, and this will give me like how many of these nodes were unique. So even though we've had 911 chef client runs, we've only had 250 actual clients checking in. And if I want to get a little bit more idea of sort of the distribution of systems, I can do things like look at the chef node platform and platform version. So this gives me a picture of, I've had 50 distinct Alma Linux 9.0 nodes, 50 distinct Amazon Linux nodes. You can tell that this is demo data by your nice round numbers here. And so you do have a way to sort of dig into that. If I want to look at like a specific chef client run, this is the trace data. This is what, when we say we want to trace, this is what we're looking at. So, I can look at the overall chef client run. I can see that it took 15 seconds. The compile phase took 7 seconds. The converge phase took 8 seconds. And then way down at the bottom, the handlers only took 105 milliseconds to run. And it goes down. So inside the converge, I have my different cookbooks. So I have my ChefConf cookbook. Then I have my OS hardening cookbook. Inside the ChefConf cookbook, I make those files. I do a sleep. I do a fail test, see like things like that. And within the cookbook, I can also see all the resources that are run for the OS hardening. You can also see, what resources were up to date, what resources were updated. Was anything skipped? So these were skipped for some reason. Over on the right side here, we may be able to see that reason, but I don't remember if that's actually true or not. Anyways, that may be an improvement we can make on the handler in the future, is to figure out why something was skipped. So this is the idea of each trace, and this is showing us sort of the number of those, and we can sort of group by or do a where clause or something like that. So if I want to see where so if I want to see chef node host name contains Alma Linux. It shouldn't be host name, it should be chef node name. So the host names are all Dokken. All right. So if I do that, I can see, specifically my Alma Linux nodes. But there's more than I can do. There's more than just counting and like seeing how things are counted. I can do, we do heat maps. So this is looking at the last 8 hours of all of the chef resources that run. I can see here that I do, for the most part, everything's down here close to 0. That's where you get those dense blue squares. But I have some things that, pop up, and some of them, are taking 140 seconds. That's a really long time. So, how can I dig into that? So one of the things that I can do is I can take some of these outliers. Let's try these guys here. And I can do what's called a bubble up. And basically that looks at what's in the box and what's outside of the box, and, shows me sort of what's different. So everything here are attributes in the trace, but they are, what's in yellow is what's unique about what's in the box. So it looks like for what I've selected, everything was Alma Linux. The recipe was the Yum recipe, which is in the OS cookbook. They were both up to date already, so that's a little odd, but let's just see what resource type they are. So I can slim this down. So they were all DNF package resources. And what was the action being taken by DNF package? It wanted to do a purge. So for some reason, this purge took a really long time. Now, this really stands out here, but maybe I want to see what the spread is on the lower line, where everything's clean. So I can do where duration ms is less than or equal to 10,000 milliseconds, sorry. So under 10 seconds. Here, I've got this weird grouping that happens right around 3 seconds every time. So let's, dig into that. Again, resource type. Okay, so these are all chef sleep commands for 3 seconds. And basically what that's saying is, that a lot of these recipes are sleeping for 3 seconds because I put that in my cookbook code. All right. So finally, the other thing I want to know is what, something like what nodes are failing more than once, right? So if I want to know how many nodes are failing multiple times, because those are the nodes you want to target for fixing, I can do that as well. So I can say the trace parent ID doesn't exist. It has an error happening. And what's the node name and node GUI, and where that count comes out to be more than one. So I've got some GUIDs and host names that all have failed multiple times. And, maybe I want to see if it's the same failure or not. So I can look at my exception data, add that in there. Again, this is my random number generated failure. So just, bad dice rolls, apparently. I should probably just take that code out of my cookbook and then I will stop having failures. Yeah, so these are the kinds of things that we want to be able to find out and ask our systems right away. Right now, I want to know what's happening in my environment. This observability from Honeycomb gives us that capability to do that. All right, and I'm going to hand it back over to Andy.
Cool. So we're going to breeze through this because it's basically the same thing, but on the inspect side. Just want to show some examples and how you'd use it. Where's my right browser? There it is. Perfect. Let me make this bigger. So we've got a Git repo for this one. It's under my name, Andy Dufour, inspect reporter Honeycomb. So it's a little easier because it's not a chef handler. It is a inspect plugin. And basically you can install this for sync auditor or inspect with your tool of choice. Plug and install inspect reporter Honeycomb. And you've got to export 2 environment variables. One is your Honeycomb API key, and one is your the API URL. It's here in the README. Real quick browse through the code. I need to be one more folder in. We've got the reporter. And basically, we're taking the output of a report, and then we're generating some trace ID hashes so that we can give it IDs. And then we structure this in a tree so that we can see it in the waterfall view like we saw on Davin's demo as well. So if you want to look at the code, it's right here. But I wanted to show you very briefly the kind of the outline and how you would view and inspect resource here and what that looks like and questions you could ask. So, first of all, you come into Honeycomb, you've got your recent traces view down here at the bottom. We can click any of these to go take a look at what a trace actually looks like. You can see that top level, we have an inspect run, and then within it, we've got the profile name. So this is Linux baseline. And then underneath that, you have all of the controls and the results from those controls. So we didn't quite get the waterfall graph lining up as nicely here, but you still do have all your durations. And if we click on this, you can see on the right-hand side here, we've got essentially all kinds of information showing up about that particular result inside of your inspect profile. This one passed, yay. And basically the code that ran, the attributes that are there, that kind of thing. So what would you do with this? Some questions I think I would ask of my inspect resources are, what's my slowest resource? So when you think about that, you'd come to make a new query, and you could do something like generate a heat map based on duration. And we only care about results. So we'll do type equals results. I need to put a space, type equals results, and we'd run that query. You can see we've got this grouping of resources. Each of these squares represents a resource that ran as part of your inspect profile, or a result that ran. This is a test essentially executing on your machine. And again, we're going to use bubble up. And what I can do is draw a box around these longer running resources. And we're going to be able to see immediately what that is. You can see resource classes there. And we've got this thing called SUID check. But something a little more interesting to me here is control ID. So we've got control ID here, and it says OS-06. And if we go, close this tab, so forgive me, but if we go to DevSec, inspect profiles, and look at the Linux baseline and the controls here, and OS spec, we're going to see OS-06 is check for SUID SGID blacklist. And basically, this would give us some cue that like, hey, this resource is taking a long time to run, or this test is taking a long time to run. We should probably go and check out the SUID check inspect resource and take a look at it and see what's taking so long. Some other questions I might ask of my inspect data, what test is failing the most? So we might go here and look at like visualize the count of where status is equal to failed. And we might group by control.id. And we might run this, and we should be able to see that, hey, of my inspect runs that have been happening, my OS-05 control ID failed 2,304 times, tied with SSH22. I'm going to kind of assume that that means they all failed in this case. They failed on every run I had going because my base image is not right. But then we could go a step further and say something like, what platform is this on? So we could do like platform.name and run the query. And we'd see that these are all Ubuntu machines. And if we go back a little bit further, say last 24 hours, we might see some other ones, like we've got some Alma Linux ones. But let's say we want to get a little more specific and we want to say, okay, we know this control fails a lot, but we want to go and find the IP addresses that are failing the most frequently. We could show only where control ID is that, and then we could group by and add host name here, and it'll show us the host names of the systems that control is failing on. So just some examples of questions you might want to ask of your inspect data once you're in there. I think that's going to bring that to an end. And Davin, I'll hand it back to you to finish off.
All righty. And so I will go back here. Just to wrap up a little bit. So Honeycomb, using these tools, we can utilize Honeycomb or another observability tool as a way to really ask questions of your chef run or your inspect run data to figure out sort of what's happening in your ecosystem right here and right now. But again, it's not long-term storage for audit purposes. That's where Automate comes in, and it can store your run data for years, or your compliance data for years, or whatever. Honeycomb just doesn't retain data that long. It really is focused on here and now. To get started on all this, you can, on the chef side, basically just add this handler and policy to your run list is like the first thing on your run list. So it'll load up quickly. You can go to github.com, tdarwin, chef handler honeycomb. Or on the inspect side, it's a little easier because we actually published a gem for that. So you just have to do an inspect plugin install, inspect reporter honeycomb, set your environment variables, and go ahead and run inspect. If you want to check out the code for that, github.com again, Andy Dufour, inspect reporter honeycomb. Thank you all so much for attending, and hope you found this useful.